currently a distinguished professor at Taiwan University, and he's have many research areas, and he's well known for his leap SVMs and deep linear. So I'm so grateful for him to come over from all the way from Taiwan and to give a speech here. So Professor Li.
Thank you. So I guess microphone is already working, so let me put this back. So it's my pleasure to come here to this machine learning meetup to give a talk. So today I'm going to talk about large-scale linear classification. And this is going to be an overview of this topic rather than like the technical details of a small part of linear classification. So I want to talk about the status and what are challenges for the future. Here is the outline of the talk. First, I will have a brief introduction. And for linear classification, optimization methods are a very important part. So I will spend some time on that. And I will show some sample applications of linear classification. Then I will briefly talk about big data linear classification, and then give conclusions. Okay, so what's linear classification? Well, basically, we mean that you are using a simple weight vector W as the model. So for binary classification, that means you have only one model vector. Yeah, because if you have multi-class, probably you need several vectors. Then once you have such a weight vector W, then your decision function is going to be the inner product between the model and the test vector X. Okay, so for any new data X, you just do the inner product and you check the sign. If it's positive, then you say this is a positive data. Yeah. Okay, so of course we know this is a very old topic, and such a linear classification technique has existed for a long time. Yeah. But even though recently there are many new and more advanced techniques which are available and are very useful, but linear classifiers, they remain to be widely used in many situations. And one particular reason is because of the simplicity. Yeah. And not only that, those more advanced methods may also be based on or partially based on linear classifiers. Yeah, so that's another thing. And in this talk, I will give an overview of this topic of linear classification. So now I want to say something about the difference between linear and nonlinear classification. Well, there are several ways of nonlinear classification. So for example, you can say that decision tree, those tree type methods, they are nonlinear classifiers. But here, when I say nonlinear, I mean kernel methods. So certainly kernel is one nonlinear classification method. So if we compare linear and nonlinear classification, here I show two figures to see their differences. So on the left-hand side, for linear classifier, basically you draw a dotted line to separate the two classes of data. But for nonlinear, you want to have a nonlinear curve to separate the data. But the way people use kernel is not by directly modeling the nonlinear curve. Instead, they map the data to a higher dimensional space. So if originally you have two features, which are height and weight, then probably you can do some nonlinear mappings to generate additional features, such as this weight divided by the square of height. Okay, by using more features, you get more information. So suppose the classifier is more powerful. Yeah. So for methods such as support vector machines or logistic regression, in general, they can be used in two ways. I mean, roughly, they can be used in two ways. So one is by kernel methods. That means, okay, now you make a data X to a higher dimensional space. Okay, so you get a new vector file of X. But this new vector is so high dimensional, so it's very difficult to handle this high dimensional vector. Then people use the so-called kernel trick. So by kernel trick, we mean that the inner product between the two mapped vectors can be easily calculated. So then you use this property to be able to still classify those high dimensional vectors. So the advantage is that you are actually classifying very high dimensional data, but the disadvantage is that for this inner product to be easily calculated, you can only use some spatial mapping function. Okay, so your mapping function must be spatial, so the kernel can be easily calculated. So this is the kernel method. But another way of using SVM or logistic regression is that you do feature engineering. So in that feature engineering process, you may already embed some nonlinear information into your features. After that, okay, because now you say my features are good enough, then I just do a simple linear classification. But this is another way of doing that. And in today's talk, I'm going to focus on the second type. So that's what we call linear classification. So you do feature engineering first, and then do the linear classification. Okay, but we know nonlinear is supposed to be more powerful, right? So why there's a reason to use linear classification? So here we need to review a bit about the idea of kernel methods. So if you are using kernel and you map data to a higher dimensional space, then your decision function, this inner product between W and the mapped vector, is going to be expensive because both vectors are very high dimensional. So the idea of kernel methods is to have this W to be a linear combination of training data. So somehow kernel methods they manage to have this property so that your weight vector is a linear combination of your training vectors. Okay. So we see this linear combination with coefficients alpha I. And once you have such a representation, then your decision function can be represented by the summation of a bunch of inner products. And each inner product is called a kernel value. So we can see that if k of xi xj is the inner product between phi xi and phi xj, then the original decision function, this inner product, now we put this summation into the decision function, then you get the summation of certain kernel evaluations. Yeah. And to make this work, you want each kernel element to be easily calculated. So you are going to use a spatial mapping function. So an example is this degree 2 polynomial kernel. So if we write k of xi xj as the square of xi transpose xj plus 1, this is actually the inner product between two vectors, where each one is in n square dimensional space. And here n is the original input, the dimensionality of the original input space. That means original you have n features, but now you have mapped the data to an n squared dimensional space. However, by this kernel, you can still do the inner product in the original space and then take square. Yeah. So this is the kernel trick. Okay, so this is how kernel works. But there's a problem. The cost may still be too high. Now, if we compare the prediction cost between using linear versus kernel. So the left-hand side is the simple linear product for doing linear classification. That's one single inner product. Okay. So if n is the number of features, the cost is order n. However, if you do kernel, now you need to do this summation. And each kernel evaluation also involves order n, where n is the number of features. Right? Therefore, the comparison is order n versus order n times L. So you can see that the prediction cost is proportional to the number of training data. But for linear classification, now that is independent to the number of data. Yeah. Therefore, if you don't use the kernel approach, instead just using linear, but after finding good enough features, then such an approach is actually cheaper and simpler. Yeah. So this is one reason to use linear classification. So now we notice that actually linear is particularly useful in certain application domains. People have realized that for certain problems, the test accuracy by using a linear classifier is almost as good as using kernel. Yeah. But if you use linear, then your training and testing speed can be much faster. And this especially happens for document classification. Now for document classification, people in general use the so-called bagel words model. That means each feature corresponds to an English word. So you have millions of features, and you have the so-called large and sparse data. Because each data instance is generated from one document. So this document may have, say, hundreds of words. So among the millions of features, only hundreds of them, they are non-zeros. So we call such data sparse data. And then the status right now is that you can train millions of such data in just a few seconds. Here I show a comparison between using linear and the kernel. So for the first part, I show the result of linear. Here time means the training time, but accuracy means the test accuracy. And then for the second part, I show the results of using RBF or say Gaussian kernel. And again, I show training time and the test accuracy. We can see that for this data set, this Cove type data set has more than about a half million training instances, but only about 50 features. The training time by using linear is very fast. So in 1.4 seconds, we have finished training those half million instances. But the test accuracy is only 76%. Now if you spend more time by using Gaussian kernel, say here you use about half day to do the training, then your accuracy is dramatically improved to 96%. So in this case, you say, well, I want to spend more time on the training in order to get a better model. Okay, but for three other problems that I highlighted here. For this News 20 data, well, from the name, you probably figure out that this is a document data set. In 1.1 second, we have finished the training and achieved 96.9% of test accuracy. But if you use kernel, then you need about 400 seconds, but the accuracy is almost the same. Take the third one called Yahoo Japan. This problem is already pretty large. It has about 140,000 instances and almost 1 million features. Then in 3 seconds, we have finished the training, and accuracy is almost the same as that of using Gaussian kernel. So this is an example to show that, well, for some problems, if their space of input features is already rich enough, then there is no need to further make data to a higher dimensional space by using kernel. Because by using kernel, your training and testing speed is actually much slower. Okay, so now we formally introduce the formulation of binary linear classification. Now we assume that there are L training instances. Actually, each not only instances. That's a pair of that's a label and instance pair. So each pair includes yi, that is the label. So yi is either plus or minus 1. Now assume we consider only binary situations. And the xi is the so-called feature vector. Yeah. So now let's assume that we have L training instances, and n is the number of features. The standard optimization problem to get a linear classifier is by solving such an optimization problem, which is the sum of two terms. The first term, that's W transpose W over 2. That's the so-called regularization term. Yeah. And today we talk about the so-called L2 regularization, because we have no time to talk about L1 regularization here. And then the second term is actually related to training losses. We have the summation over training data, and then for each I, this function somehow indicates the training loss at the ith data. And there's a parameter C, which is usually called the regularization parameter, to balance between the two terms. The reason of doing that is that you want to avoid overfitting, but also avoid underfitting. Yeah. So this is the standard way of doing binary classification. There are a bunch of commonly used loss functions. So the first one is called the hinge loss. So for the hinge loss, basically we take the max between 0 and 1 minus YW transpose X. So why that? Because we are supposed to hope that our model W can generate, can lead to W transpose X has the same sign as Y, right? Because if Y is positive, you hope W transpose X is also positive. So this YW transpose X, we hope that it is positive. But if it is negative, that means a wrong prediction, right? So 1 minus the negative number becomes positive. So after the max function, that means that indicates there is a training loss. But otherwise, if you have a positive value here, 1 minus positive is negative. After taking the max function, that is 0. That indicates 0 loss. Yeah. So this is the so-called hinge loss, or we call it L1 loss. The second one is called squared hinge loss, or we can call it L2 loss. That's simply the square of the first. The third one is log and exponential, is called logistic loss. So in fact, if you are using the first two, they are the linear support vector machines. They are linear support vector machines. And the third one is simply logistic regression. But notice that my formulation here is slightly different from the standard way people talk about support vector machines. Because in general, for historical reason, people put a bias term. So the decision function is W transpose X plus V. Yeah. But in a high dimensional case, such a bias term may not be needed. Let's compare those three loss functions a little bit. If we draw the figure of the three loss function, so now the x-axis is minus YW transpose X. So we hope this, because we hope YW transpose X is positive. So after taking the negative, we are hoping that it is negative. Now we can see that on the left-hand side, when the value is negative, the value is really close to 0. So that indicates no training loss. But on the right-hand side, now there are training loss. Okay, but they are actually very similar, because on the left-hand side they are basically just 0. Okay, so only for the training error they put a different penalty. Yeah. Therefore, from this figure, probably we can say that in general the performance of using those three loss functions should be similar. Yeah, that's really the case. So in general, okay, except some spatial problems, in general, if you apply linear support vector machines and a logistic regression, the performance is actually similar. Yeah. However, we notice that their optimization methods may be different because of their different differentiability. If we go back to the formulation of the three loss functions, logistic loss is twice differentiable. But the first two, especially the hinge loss has a breakpoint here, it's not differentiable. Okay, so now to get the classifier, we need to solve the optimization problem. So I will briefly talk about optimization methods. But now you say, oh, this optimization problem of W is just a simple unconstrained optimization problem. Well, that's right. So in principle, any unconstrained optimization methods can be applied. Yeah. But of course, whether they are efficient enough, that's another issue. But there's a special, but I want to particularly mention the difference between linear and the kernel here to explain why we can achieve much faster training for linear rather than kernel. We mentioned earlier that if you use kernel, then your model W is actually a linear combination of training vectors. Then you have to work on the coefficients alpha. Okay, because phi of xi is so high dimensional, maybe even infinite dimensional, you can never write down the vector W. So all you can do is to rely on storing and manipulating the coefficients alpha. So what's the problem? The problem becomes that when you are trying to get the model, all you need is to get the alpha. So this is more restricted, right? Okay, because you cannot directly minimize a problem of W. You need to minimize a problem over alpha. Okay. That's a restriction. But now for linear, we have no such a restriction. Okay. Because now for linear, this W is finite dimensional, so you can directly minimize the problem of W. But alternatively, you can still work on alpha. That is okay. So for linear classification, it's more flexible to choose optimization methods to find the model. Now, among different unconstrained optimization methods for to solve our problem, in general, in optimization, you can categorize problems to like low order or high order optimization methods. So low order, we mean that you only use first order information like gradient, or not even use gradient information. That's what we call low order methods. The special property of such methods is that you can quickly get an approximate solution, okay, a very rough approximation. And because now an approximate solution can already lead us to have a model. So now you can quickly get a model, but usually you get very slow final convergence. That means if you want to accurately solve the optimization problem, this type of methods is going to be slow. In contrast, if you use high order optimization methods, that means you may use second order information, like the second derivative. Such methods are often more robust, yeah, and useful for yield condition situations, but they cannot quickly give you a model. Yeah, so that's the difference. I will give examples of each type of methods. And I would like to argue that both types of optimization methods, they are actually useful for linear classification. I'm just in different situations. So here's the first example. Okay, I want to do the optimization using second order information. So this is second order method. Well, in optimization, second order method, that actually means Newton method. So what's the basic idea of Newton method? Basically, you want to find a Newton direction. That is the solution of the second order approximation of the function value. Suppose WK is your current solution. Okay, the current solution. Then this function of S is the second order Taylor expansion at the point WK. So now I minimize the subproblem over S to generate a direction S. Then using that S, I can update W. So that's the basic idea of Newton method. And solving this subproblem is equivalent to let the derivative to be 0. So if we calculate the derivative of this second order approximation, we actually get a linear system. So this is often called the Newton linear system. On the left-hand side, we have the second derivative of the function, which is usually called the Hessian matrix. So we have the Hessian matrix times S equals minus gradient F. So suppose we are able to solve this Newton linear system, then we'll get a direction, and we can update the W. Unfortunately, this Hessian matrix is simply too large to be handled. Okay, what's the size of this Hessian matrix? Well, it's the same as the dimensionality of W. That means the same as the number of features. So it's n by n, and n is the number of features. So if you have 1 million features, then you are going to handle a 1 million by 1 million matrix, which is almost impossible. However, here we can use some special properties of the optimization problems. For logistic regression or the squared hinge loss function, after some calculation, we can find out that the Hessian matrix actually has a special form. So it is the summation between the identity matrix plus the regularization parameter C times the transpose of data matrix as X transpose times the diagonal matrix D times the data matrix X. So here X is simply the collection of all the training data. So I call it the data matrix. And D is a diagonal matrix. So once we know that, once we know this, then we can use a special iterative method to solve this linear system without even explicitly forming the Hessian matrix. So the idea is, for this iterative method called the conjugate gradient method, it is a commonly used iterative method to solve a linear system. So that's an iterative process. At each conjugate gradient iteration, all you need is the so-called matrix vector product. Now the matrix is our Hessian matrix, right? So all you need is the Hessian vector product. And we notice that because earlier by our calculation, we show that the Hessian matrix is the product of X transpose D and X. But now you don't need to really calculate the product of those three things. All you need is to sequentially calculate matrix vector product. Now if we want to calculate the Hessian multiplies with S, then all you need is to multiply this X and S. Then you get another vector. Then you multiply it with a diagonal matrix. Then multiply it with X transpose. And are we able to handle that? Yes, because of course you must be able to store the data matrix X, right? So X must be somewhere, right? That's the assumption. Okay. So you do have X somewhere, and because we are able to do such a sequence of matrix vector product, we are able to finish the Hessian vector product for one conjugate gradient iteration. Then after several conjugate gradient iterations, you get a solution of that Newton linear system. So the optimization area, this is a so-called Hessian-free optimization approach. Okay, so here we have briefly talked about this optimization method of using second-order information. Now let's switch to consider a first-order method. Now I consider the dual problem of support vector machine. Okay, so now this is an example that instead of working on W, we work on the loss coefficients alpha. The dual problem of support vector machine is to minimize a function f of alpha, and alpha takes such a form. So you have alpha transpose Q alpha minus the summation of alpha. So each component of the matrix Q is actually the inner product between two training vectors. So this is actually almost like kernel. So in the kernel case, this Q is the kernel matrix. Right? But now we are doing linear. So Qij is simply the inner product between two training vectors. But let's not worry about how this dual optimization problem is obtained. So we basically have a quadratic function of alpha. And also, those alpha, each alpha I is in a bounded region between 0 and C. So that's the so-called bounded constraints. So now we have such an optimization problem. Then now we plan to use a first-order method, which is called the conjugate gradient method. So we are going to apply a conjugate gradient method to solve such a problem. And here I give a formulation of L1 loss. But if you are using L2 loss or logistic regression, the situation is similar. And the idea is very simple. For Gaussian descent method, this is a very simple and classic optimization technique. The idea is that at each step, you basically fix all the variables except one. So you try to change one variable by fixing all others. Right? So mathematically, that means you can define an indicator vector EI. For this EI, the ith component is 1, and for all other components, their values are 0. So you minimize a single variable optimization problem from the current alpha. You plus the direction D times EI. But because EI has basically all the values to be 0 except the ith component, so you try to change the ith component with the amount D. Okay, so you minimize this one variable function of the variable D. After some calculation, we can easily show that this becomes a simple one variable quadratic function. We have a D squared here, and you time it with the II component of the matrix Q, and plus the ith component of the gradient times D plus constant. So everybody knows how to minimize a one variable quadratic function. It has a closed form solution, right? So we have optima D to be like this. But of course, now we need to take the bounded constraints into consideration. But this is very easy. You just do a projection. If it is less than 0, you project it back to 0. If it is larger than C, then you project it back to C. So now we have the whole method. Such a method is actually very effective to train a linear classifier. But of course, there are some other other considerations, but I don't have time to show that here. But basically what I want to show you is that now we give two examples. The first one actually is a high order method that tries to use second order information. But here, as you can see, all you need is the gradient, right? Is the gradient. Therefore, we are using the first order information. This is a lower order optimization method. Now let's do some comparisons. So let's try these L2 loss support vector machines. And I compare a bunch of methods. The first one is called dual coordinate descent method. That's the method I just mentioned. We solve the dual, and by using this coordinate descent approach. Well, let's not worry about what this the second is. This is actually a slight improvement of the dual coordinate descent method. The third one is also coordinate descent method, but it is by minimizing the primal problem. So by primal problem, I mean the original problem of W. And then the fourth one, that's the Newton method. That's a particular type of Newton method called trust region Newton method. Okay, so that corresponds to the second order method I just mentioned. So now we have the results of several problems. The x-axis is the training time in seconds. The y-axis is actually the difference to the optima objective function value. So that's the minima of f of w, to see how good our solution is. So y-axis is the distance to the optima, but x-axis is the training time. So if you spend more training time, then the difference should become smaller. But this is log scale, so actually in this place, the difference is very, very small. Yeah. Okay, so now if we check this RCB1 data set, it has more than 500 million documents. But in actually this is 3 seconds. Is here this is 5 seconds. So actually in 2 or 3 seconds we have finished the training. And what is this method? Those two curves, they correspond to dual coordinate descent methods. So coordinate descent methods by solving the dual problem is very useful in such a situation. And for the green line, so this green curve, that's the Newton method by using higher order information. So you can see that it doesn't give you a good approximation quickly. Yeah. But you know, in the end, the final convergence is actually very good. Say, if you look at this curve, so in the end, the curve will be almost vertical. The final convergence can be very fast. Yeah. But this is an example to show you that seems like the low order methods are very effective in such situations. However, we want to give another example. The results are the opposite. Here I have another data set. This one has basically about 32,000 training instances, but the number of features is only about 123. And again, we compare those 4 methods. In the previous slides, the blue curve is the dual coordinate descent, which is very good. But now we can see that it is here. It is much slower than the Newton method, which is the green curve here. So for this example, actually the green curve performs the best as the second order methods. Yeah. Yeah, of course, there are some reasons behind this. So this is the left-hand side is the figure of showing the distance to optima versus the training time. But I also draw another figure to show you the test accuracy versus training time. Okay, because you may argue that, well, for those blue curve, at this point the model is already good enough, but that's not the case. You can see that in the early stage, their test accuracy is simply not good enough. Okay. One reason to explain why for this data set you need to solve you don't want to solve dual coordinate descent is because the number of features is so small. So if you solve the problem of W, the dimensionality of W is the same as the number of features. That's 123. So you have 123 variables. But instead, if you solve the dual problem, the size of the dual problem is proportional to the number of instances. Well, in this case, that's 32,000 variables. That's a lot more. So that partially explains why for this data set, if you use the dual quotient descent, it doesn't work very well. But my conclusion is that, in my opinion, for linear classification, both types of methods, low order or high order methods, they are useful in different situations. Now let's move on to talk about some sample applications. So I will show two applications. So the first one is for a natural language processing application called dependency parsing. So this dependency parsing is a natural language processing application. Let me show some original results of using kernel. By using kernel, I can use RBF or Gaussian kernel or degree 2 polynomial kernel. My training time is about 3 hours. And for the parsing speed, okay, I use the result of using degree 2 polynomial kernel as the standard unit of the testing speed. Because for this real application, I cannot show you the real testing time now. Okay, so now if this is called the single unit of the testing speed, then this Gaussian kernel is actually slightly slower. That's 0.7. Okay. And this UAS and LAS, they are like the test accuracy. So we achieve like 91 something. Okay. But we are not satisfied about the training time, so we go to use linear. If we use linear, we just apply linear classification. Now you can see that the training time is dramatically reduced to 3 minutes. Okay, so that's 60 times faster. And how about testing speed? Well, that's even better. That's almost 2,000 times faster. Yeah. Well, the reason is obvious, because we mentioned that you only need one inner product, but for kernel you need many inner products. Right? However, the accuracy is not good enough. Okay. Now this is only 89. That's 2% worse than if you use degree 2 polynomial. So what can we do? Well, we do a trick. We explicitly represent degree 2 polynomial expansion of data. Then that becomes our new data. Then we train a classifier. So by doing that, our training time here is 3 minutes. So this is still very fast. And the testing speed is 100 times faster than if we use kernel. Yeah, that's actually the most important thing for this application. Is about testing speed. So if we use kernel, then because you need to do a lot of inner products, well then that's not good. But now the testing speed is a lot faster, and also training is much better. But now you may ask a question: why the training time of linear is the same as after you have done the degree 2 polynomial expansion? Well, the reason is because they are trained under different regularization parameter C. So remember, there's a parameter C, which balanced between regularization and the training losses. They are under different C parameters. That's why, because otherwise, if under the same parameters, this degree 2 polynomial here should be the training time should be longer. Okay, so what we have achieved? We get faster training testing, but also maintain good accuracy. So exactly how we achieve this? So now we consider the so-called low degree polynomial mappings. This is basically the pairwise product between all your features. So your number of features becomes what? Becomes order n squared, where n is the number of original features. By such combinations, you get n squared features. Yeah. Now you see, does this work? Because now your number of features becomes so large, right? And earlier, when we say linear is better than kernel in terms of testing speed, we use order n to compare with order n times L. Okay, because for kernel you need a bunch of kernel evaluations. Now you say, well, the comparison is no longer n versus n times L. It's n squared versus n times L. So you may not get any advantage, right? If n is very large, because n squared may not be smaller than n times L. Well, true, but That's not the case for sparse data. For yours, if your data is very, very sparse, then this n is not n, but should be n bar, where n bar is the average number of non-zeros per instance. Right? So it's a lot smaller than n. Yeah. So essentially, you are comparing order n bar squared versus this L times n bar. And because n bar is usually very small for sparse data, then it is okay. So now let's see the statistics of this data set. Right. This is actually a multi-class problem with sparse data. Originally, the number of features is almost 50,000. So if you do degree 2 mapping, the dimensionality is larger than 1 billion and 1 billion. And L is the number of training instances, that's 200,000. But n bar is very, very small. On average, one instance has only 13 non-zero values. It is so sparse to the point that after degree 2 polynomial mappings, many features, they never have non-zero training feature values. Okay. So after this polynomial mapping, a lot of feature columns are in fact entirely zero and can be removed. Therefore, among the 1 billion features, only slightly more than 1 million, they have non-zero values. So essentially, we have a problem of so many features. Yeah. So we can do the training. Yeah. But of course, how to handle such things, you also need some techniques. Yeah. But this is an example that, okay, because this problem is so sparse, then we can do this kind of low degree polynomial mappings, and we train a linear classifier, and we can achieve these better results. A faster training time and a faster testing speed, but also the same accuracy as by using kernel. Okay, so some discussion. Well, we have a Journal of Machine Learning research paper to show you all the details. But now you have a question. If after this kind of low degree polynomial mapping, then the data will be very high dimensional, right? Okay, so then how to handle that? So of course, people understand such a difficulty. So they propose some kind of projection or hashing techniques. Okay. So it's like you map data to a higher dimensional space, and it's so sparse. You just do hashing techniques to map the data to several bins. Yeah, that's the idea. So there are some related works here. And in real application, this is used in computational advertising. Okay, so for many CTR, click-through rate prediction applications, they do use such techniques. Okay, let's move on to another also interesting application. That's for transportation mode detection in a sensor hub. So in this real application, we actually deploy a linear classifier in a sensor hub. So for this job, we want to put the classifier in a very small device. And this one has only 16K of RAM of memory. Now if we for the data set, we train a regular classifier. So let's see what the model size is. So if you use decision tree, then you get then you need like so much model size. And then if you AWS with several trees or SVM with Gaussian kernel, then the model size is much larger than the 16K that we can afford. So we need to find some ways. Okay, and for this data set, the number of features is only 5. So then what we did is to consider the degree 3 polynomial mapping. So what's the dimensionality after doing a degree 3 polynomial mapping? That's actually 5 plus 3 to choose 3. Well, in this place, our decision function actually has a bias term, so we plus 1. So this becomes 57. So in the end, we have a linear classifier of 57 features. Yeah. So what's the size of the model? This is again a multi-class problem. So for this multi-class problem, we use the so-called 1 against 1 multi-class strategy. That means if you have 5, then you do pairwise binary classification. So you need 5 choose 2. You have 10 models. Then 10 models times 57. And if we use single precision, then the model size is is less than 3 KB. So that is small enough for us to put the classifier into this device. So in fact, even though this one is 16, but because other jobs are also running and also for the operating system, then actually the amount of RAM that we can use is actually much less than half of 16K. So now you may ask a question, why we are considering this 1 against 1 strategy? If you use the so-called 1 against the rest, then for 5 class problem, you actually have only 5 binary models, right? Because you have like class 1 versus the rest, class 2 versus the rest. Well, of course, we tried that first, but somehow for this problem, 1 against 1 gives slightly better accuracy. Okay, but because we can afford a larger model size, so that's why in the end we do this. Okay, so this table summarizes the results. If we use Gaussian kernel, or say RBF kernel, the test accuracy is really good. It's 85%. That's the best. However, the model size is too large for our device. Now, if you use linear kernel, the model size is really small. You only need to store 5 features, right? Plus the bias term. So that's 6 components. That's enough. Right? So the model size is really small. However, the test accuracy is not good enough. You need a certain nonlinearity. Right? So by using the trick, we say, okay, we do degree 3 polynomial mapping to expand the features, okay, to get the nonlinearity. However, we still train a linear classifier. Right? So the model size is still very small. However, the test accuracy is almost as good as by using the RBF kernel. This is very good, because usually you don't achieve that. Okay? Because when you apply the low degree polynomial mapping, you don't know whether your accuracy is closer to Gaussian kernel or closer to linear. In this case, this is a good case where the result is closer to using Gaussian kernel. Yeah. So this is a good situation. Okay, so I have about maybe 10 more minutes left. So I want to briefly. So I think we do 1 hour. Okay. Well, I plan to do 1 hour talk. So.
You have time.
But then we also leave some time for questions. Yeah. Because I want to hear your comments. So I want to briefly talk about big data, linear classification. Well, this is still an ongoing research area, and also I also spent some efforts on that. So the reason to do big data linear classification is that nowadays, our data can be easily larger than the memory capacity. Yeah. Because traditionally, for all the traditional machine learning methods, they assume that data can be stored in the computer memory. Right? So what can we do if the data set is larger than the memory capacity? Well, one thing you can do is to do disk level linear classification. Okay? Because usually the disk size is bigger than the memory size. Yeah. But of course, accessing data from disk is very slow. So therefore, we need to design methods which are smarter to reduce the number of data accesses from disk. Yeah. So earlier we actually have a paper and a small package for that. That is actually quite useful in some situations. So for example, recently we released a data set of about 600 gigabytes. So that's the largest public available data set that we have released so far. That one is 600 gigabytes. However, for my machine has only like 80 gigabytes of RAM. Okay, and I need to apply this tool to do the training. It works quite well. Okay, but if the data is even bigger than the capacity of disk, what can we do? Well, we need to do distributed linear classification. Yeah. So this is recently an active research topic. So how to do the distributed training? Well, basically you can just try to parallelize all the existing machine learning methods, or say all the existing optimization methods. But the problem is that some of them can be more easily parallelized, but some of them are difficult because they are sequential in design. Remember, we gave 2 examples, right? The first one is a Newton method. The second is a coordinate descent method. That coordinate descent method is inherently sequential. unless you do some modification. Okay, but otherwise you cannot directly parallelize it. It's not going to work. No. But anyway, among the existing methods, some of them can be directly parallelized. An example is the Newton method that I just mentioned. So recall that in that Newton method, at each conjugate gradient iteration, all you need is the Hessian vector product. And that turns out to be a sequence of matrix vector multiplication. You multiply x times s, okay, then another x transpose times a vector. Such matrix vector product can be run in parallel. So we can do parallel Hessian vector products. Right? So the idea is very simple. Your data matrix is now distributedly stored, so say 2p parts. So then the original Hessian vector products that you hope to calculate can be done so that the first node calculates part of the Hessian vector product. Then you do a reduce operation or an all reduce operation to get a sum. Yeah. So that is very easy. Yeah. While this looks easy, but there are many considerations. So for example, now data are distributedly stored in different machines. The example that we just mentioned is a so-called instance-wise data partition. Okay, so you assume that each machine stores a subset of training instances. However, you can do a different way by splitting data by features. So that means each node stores part of the features, right? But actually their communication cost becomes different. Even though I don't have time to show details here, roughly what I can say is that if you do instance-wise data split, then your communication cost. So where do we have communication cost? In this summation, we have communication cost, right? This is an order. This is actually an order n vector. Yeah, this is actually an order n vector. So now you have a bunch of order n vectors. You want to group them together, and also maybe broadcast the resulting vector to all machines. Yeah. So for instance-wise split, the amount of data that you need to move from one machine to others, that's order n. But if you do feature-wise, that's the other thing. That's order m. That's related to the number of data. Yeah. So in that sense, you need to, depending on your data, whether your number of instances is more or you have more features, then you choose how to split your data. But that's also related to how originally your data are stored. Yeah. Another issue I want to mention is that, in fact, deciding we should do distributed training or not is already a difficult issue. Because in linear classification or any other classification problem, you can always subsample data to one machine for deep analysis, right? Because like on one machine, then you can apply more advanced methods, right? So it's possible that you spend a lot of efforts to do distributed training using all the data, but then the result is even worse than you using some sophisticated technique on one machine, right? So this is actually always an issue. So it's not clear yet for which area that distributed training is more suitable. Okay. But we already know some areas. One particular example is this click-through rate prediction in computational advertising. There are several reasons why this has happened. Okay. First, now almost I think in most companies, for CTR prediction, they do logistic regression or other types of linear classification. Yeah. And this type of methods is simple enough to be run in parallel. So that's one thing. And the second is that for CTR prediction, usually you need to repeat your training procedure after a certain period of time. Say, for example, you use the data from the past week to train a model for the prediction in the next day. But tomorrow you are going to train another model, right? Okay. So you need to train models basically maybe every day or every week. So it's not good to reduce data to one machine for training and then reload that model back to the distributed system. It's more convenient to just to run the whole thing in the distributed environment. So that explains why CTR has been a very successful example of distributed linear classification. Yeah. But for distributed linear classification, platform issues are certainly important. So recently, for the above mentioned Newton methods, we have done this MPI and the Spark implementations. Actually, we are hoping to put less Spark implementation into this MLlib. Yeah, well, some works still need to be done. And what are other distributed linear classifiers? So VW from Yahoo and Microsoft is one publicly available example. It is a linear classifier. It's a linear classifier. So the optimization method behind it is to run some low-order optimization methods, stochastic gradient first at each node. Then they run a cosine-Newton optimization methods, and in the end for faster convergence. So Symbol from Google, that's another example. It's actually also a linear classifier. Yeah. But there's a problem is that actually when we work on say the Spark implementation, so now for we machine learning researchers to develop those machine learning code, we find out that those platforms are still being rapidly changed. So that's sometimes an issue, and you want to be very careful about different implementation techniques. Because sometimes, if you are not careful and you don't use a good way of doing the implementation, then your resulting code can be like 1,000 times slower. Yeah. That actually happens. Yeah. Another thing I want to discuss about a distributed classification is about batch versus online learning. So traditionally, on one computer, people often do batch learning rather than online learning. Well, the reason is obvious. Now, on one machine, okay, the data is not too large, so I try the best to use all the data. I can afford doing that. So that is reasonable. Even though by doing batch, the accuracy may not be better than online, but you still just do it. But now, in a distributed environment, maintaining those data is actually a lot more difficult. So it's possible that, I think for big data applications, those online and streaming learning can play more important role. Yeah. But it's not very clear about the situation, but certainly that's possible. And another issue I want to mention is that right now, when I say we try to parallelize the Newton method, that's actually a synchronous parallel algorithm. So what I mean that when you do parallel matrix vector product, so you have several nodes. Each node is responsible for calculating part of the matrix vector product. You need to wait until all the machines have done the job, then you do a reduce operation. Right? So that's a synchronous parallel algorithm. But for some problems or some system configuration, the synchronization time can be so huge to the point that the whole algorithm becomes very slow. So in such situations, probably you want to design some asynchronous distributed training algorithms. Yeah, but the problem of doing asynchronous algorithm is that you need to prove the convergence. So then it's like the algorithm becomes new, and you need to check the convergence issue. Well, so my belief, okay, my personal opinion is that only for maybe for some particularly large and difficult problems, then probably you want to use asynchronous methods. But for some medium-sized one, then the synchronization time is not too bad. The scalability is okay. Then you can still use those synchronous algorithms. Okay, so now let me give some conclusions. How about resources on linear classification? Well, today I talk about linear classification because this is very related to my research in the past several years. So since the year of 2007, we have been actively developing a software called LibLinear. That's for large-scale linear classification. And as I mentioned, recently we have extension for distributed training. So this is on one machine, if you want to do linear classification, this is something you can use. And earlier we wrote a survey paper on linear classification. It has a lot of references. So if you want to know the past literature on linear classifications, so from say optimization methods to how people handle multi-class classifications and a lot of other issues, you can try to check this paper. So here's the conclusion. So of course we know that linear classification is a very old topic. Yeah. But recently, because of the internet applications and maybe also in other areas, because of those new and interesting applications, so linear classification becomes useful again. But I'm not saying that kernel methods are not useful. No, kernel methods are still useful in many applications. Okay. But what I want to say here is just that if you do feature engineering plus linear classification, they can be suitable for certain applications. So I do believe that linear classification will continue to be used in situations ranging from, like in my example, like small model to some very big data applications. Yeah, so finally I need to acknowledge some of my co-workers, especially my students. They have contributed a lot to my research. Actually, some of my former students, they came here, even though I didn't tell them that I'm here today, but somehow they saw the announcements. Right. And also I thank the funding support from our government agency. Okay, so that's my talk, and thank you very much. So any questions or?
Can we get these slides? Can we get these slides?
Slides? Oh yeah, sure. I can put the slides on my webpage. Okay. So that answers one question. I think you first. Sorry.
When you do the low-level polynomial re-engineering of your features,
Yeah.
aren't you kind of? Your features aren't separate; they're not independent anymore. So aren't you kind of? Is that not a factor?
Maybe you want to repeat.
When you're talking about doing a low-level polynomial, basically multiplying your features together to create more n-squared features, aren't you reducing the independence of your features basically by really mashing them all together, and doesn't that blow up the classifier?
Yeah. Basically, okay, I do have my problem. So the reason of doing usually if you do feature combination, conceptually you think you get more information. Right? So the dependency between features can be considered. That's actually one reason of doing that. Yeah, but it's also possible that maybe because some features are noisy, but by doing so also introduce noise. That's also possible. Yeah, that depends. But in general, yes, by such combination, you get the relationship between features.
So it amplifies the effects of all of them, but the outcome is that you'll have more features in general, so it's better.
Yeah, that's right. Conceptually, that's the case. Yeah. Okay, so here.
So how about the categorical features? Also, does this conclusion apply for the numerical predictions?
Okay. Yeah. Okay, so her question is like how to handle categorical features. Well, in my talk, I didn't separate the numerical or categorical features because they are just values in my representation. So usually the question is like how to represent a categorical feature in this kind of feature space model. Well, let me give a real example. In computational advertising for CTR prediction for categorical feature, they just represent it as a sparse subvector. So for example, now if you have say if you have say 1,000 advertisements, okay, that's a feature. That's the ID of the feature. Then basically use 1,000 features. So only one of them becomes non-zero. So you get very sparse data. You get very sparse data. That's the way people used.
0, 1.
Yeah, that's 0, 1. And basically you have all the values to be 0 except only one one feature is one. Yeah. For click-through rate prediction, that's what people do. So in quite a few situations for linear classification, that's the way to represent categorical features.
How about regression?
Yeah. Today, the answer is today I didn't talk about regression at all. But so for regression, basically the change is that the label vector y is no longer plus or minus 1. It becomes a real vector. And basically optimization methods I mentioned here can still be applied. So in our software linear, we do support regression. We do have regression. Yeah. So optimization methods are similar. And for applications, you may also do feature combination and hashing and all those things. I think those are also possible. So any more? Yeah. No, you need to turn it down.
The example of feature engineering that you offered didn't seem to handle non-monotonic relationships. Am I correct about that, or would the relationships, such relationships, be possible?
Well, sorry, I don't quite understand what you
If the relationship between the predictor and the outcome was U-shaped.
But you're talking about the outcome.
Yeah.
So that the label. Okay. That's okay. Well, so I talk about classification, and the previous question is about the regression. Actually, you are talking about something else. So there's another type of problems called ranking. For example, like for ranking, the outcome has certain order relationship, right? Yeah. So then the question is how to handle such a situation. Well, the answer is well, of course you need something to handle the label part, but after that the optimization techniques are still similar. Actually, we have done some studies. So now there is a linear extension for ranking. Yeah. So there are basically three types of approaches for ranking problems. One is the so-called point-wise. So point-wise ranking means that, so now if you have, say, a rank of 1 to 5, then you do a regression so that your function to approximate the value of 1 to 5. Okay, so that's one way. Another is called pairwise ranking. So that means you try to model the relationship that 5 is better than 4, 5 is better than 3. So you try to put such pairwise ranking information into your model. That's basically what the rank SVM is doing. Yeah. And another is called list-wise approach. That means you consider the whole list into account. That is more complicated. Yeah. And you may know that, well, not recently, but a few years ago, there is a Yahoo Learning to Rank challenge. And for that data set, the number of features is not very large. It's not very large. And the winner, okay, basically the winning teams, they use tree-based methods and use point-wise approach. So basically they run random forest or gradient boosting decision tree, and they get quite good results. But such data sets may not be good to use linear classifier, because as we can see that linear classifiers are particularly useful for very large and sparse data. So probably if later on you have a ranking data with many sparse features, then using a linear rank SVM or a rank logistic regression can be useful.
Other questions?
Earlier in your talk, you gave an example of problems where linear classifier was at about the same accuracy level as the kernel method, and a problem where there was significant loss of accuracy in linear classifier. Have you done some analysis of how to identify these types of problems early without spending the time to train the kernel method?
Yeah, that's a good question. Yeah, that's good. Yeah, this is also a difficult one. So usually, if the data has very a small number of features, then probably you can guess that directly applying a linear classifier is not enough. So you have so many features, but very few, so many instances, but very few features. How can you just use a linear model to try to classify them? So underfitting tends to happen, right? So in such a situation, you want to do some nonlinear mapping, especially like kernel. Yeah. Lastly, for the example that I gave, so the first one where linear is much worse than kernel, that one has 500,000 training instances, but only 50 features. That's a situation where kernel tends to be useful. So that's one indicator. Usually that's one indicator. But for others, I don't have a good answer. Probably you want to try a linear classification. Try a linear classifier first. So if the results are satisfactory, then you don't need to do anything else. Then you can. But usually that's the case. Even for feature engineering, then there's no direct way to directly give you good features. Yeah. But sometimes right now, like some people they use deep learning to generate features, then apply linear classification. That's possible. Yeah.
When you're doing online classification, so you're kind of streaming your data, when you're learning this sort of linear classification, the first thing they tell you is like, well, you have to scale your data. You can't have one term be between 0 and 1,000,000, the other term between 0 and 100. So you have to scale everything down to 0 to 1 or negative 1 to 1. But when you're doing online stuff, that's obviously very difficult to do because you don't know what the macro. So how can you deal with that, or do you not deal with it?
No, you can still do that. So what you can do is that probably after 1,000 or 10,000 data, then you roughly know the range of features. Then you just decide a scaling vector.
So take a sample and go from
Yeah. You decided a scale. Because all you need is to decide the so-called scaling factors. There's no definitive rule to say I want like what's the maxima, what's the minima, so I can reduce the feature value range to 0, 1. Right? Because you don't know what the values are in the future, right? But in general, the purpose at least in kernel methods, the reason of doing feature scaling is for some numerical reasons in optimization. That's one of the reasons. So if you have done suitable scaling to make data to a reasonably small range, that's usually enough. So in that situation, if you do online, you just check the first several data and you roughly have an idea.
What about if your data is like on a logarithm?
If your feature data is logarithm exponential, something like nonlinear,
that would be different.
But do the same thing, sample it, and then take the.
Yeah, you can do that. That would be different. But another thing for linear classification is now for those document data, we don't do feature-wise scaling. We do instance-wise scaling. We normalize each instance to the unit vector. This turns out to be very useful for document classification. Yes, then this one will work for online classification. Just normalize that instance.
Do a hash.
Yeah. Okay. So there's one over there.
Hi there. I'm kind of interested, there's been in your talk where you talked about big data, and when you have data sets, training data sets that are so big that they exceed your 80 gigabytes RAM on your machine, it's maybe data sets with hundreds of gigabytes of data. Do you think that if you've got so much data, that sort of linear methods are the right fit for such massive data sets? Like, will you get an incremental increase in your classifier accuracy for a linear classifier with so much training data, or will you sort of have fitted your models mostly when you have those sort of like billions or tens of billions of data points? Do you need to go to like, hundreds of billions or trillions of training points? Like, for linear methods, will you see an increase in accuracy, or will you kind of have fit your model well enough with a sample that'll fit an 80 gig of RAM? What's your sense on that?
No, you say that after so many data, then you worry about linear classifier doesn't fit the data well or fit the data too well.
Will there be an improvement for sort of a relatively simple method like this with incremental data?
Okay. So basically what you are saying is, because the model is a fixed type of model called linear classifier, now just increase the data, then probably you don't get much. Right there. I basically I agree. Yeah, it's very difficult to decide like how much data you need. I think for the CTR prediction, I believe in some situation essentially probably the data which can fit in one machine is enough. That's just because that maybe they can use more, and also the whole flow is in a distributed environment, so they do that. Yeah. So I mean it's difficult, but I think there are certain problems where you still need large data. But anyway, deciding how much data you need is a big issue. That's a big issue. Yeah, that's it.
So I have questions around imbalanced classes and cost-sensitive learning, situations where the minority class being able to reach a reasonable accuracy of the minority class is very important. How do you deal with those situations?
Okay. So usually the first thing is you don't use accuracy as the evaluation criteria anymore. Because now if your data set is so balanced, then you want to use like area under curve or area under precision recall curve to better show your performance. That's usually the first important thing you have to do. Then you need to adjust your model to try to achieve better area under curve, under the ROC curve. There are several ways to achieve that. So for example, you may have to do so-called negative subsampling. So you have so many negative data, but very few positive. Then you don't need so many negative data. Right? So you subsample some negative data. Take CTR prediction as an example. There are very few clicks, so they subsample those non-click data. So that's one thing. Another is that you can give the class weights in doing linear classification. Now if positive is more important, then you give a higher weight. So remember we have a regularization parameter. Then for the positive class, you can put a higher weight there. But the problem is not easy to adjust that weight, and that's the difficulty. So in general, I still think it's not easy to handle those imbalanced data. But there are several ways. I always say that evaluation criteria is the first thing to decide. That's very important.
Professor Lin, great talk. How do you, well, this is for multi-class problem. What about having also multi-label? How do you
okay. So his question is about multi-class versus multi-label. So multi-label means that each a data instance may be associated with several labels. Yeah. So for example, a document may be both related to politics as well as sports. So there are several ways, just like this, an extension of that one against the rest or one against one. You can extend those things to handle multi-label problems. That is possible. However, but of course it is more difficult than multi-class problems. My experience is that if your number of labels is not very large, then that's still easy to handle. But nowadays there are several, say for example, if you have data in a product hierarchy. So now in any e-commerce company, then their product hierarchy may contain like 20,000 classes, and they are multi-labeled. Those kind of things are very, very, or say the hierarchy of Wikipedia. That is very difficult. So now I know data are available, but no good solutions yet. There are some competitions on that, but if you look at their results, right now the performance is just not good. Yeah, so that's still a research issue, but very challenging.
So you mentioned the data set of 600 gigabytes, right? So it seems to me you could compute the kernel matrix offline for that data set, and then just use it as a pre-computed kernel option for your existing live SVM software. And then you don't need any fancy new algorithms.
That one is 10 million instances. So if you pre-compute the kernel matrix, that will be 10 million by 10 million. No, I think that's more than several terabytes.
But in some cases, let's say the number of instances was 10,000 or so. You could compute kernel, right?
Yeah, that's right. So there's for certain problems like microarray data, you have very few instances but many features. Then in those cases, then yes, you can use kernel. But we can also say that because you have so many features, why do you need kernel? Because you have enough features, right? So you can just use linear. But those data, because number of instances is small enough, usually they can be easily handled in one computer. So I still think linear is okay. So for those problems, the challenge will be on the selection of features. For those problems, you want to apply this L1 regularization to select a subset of features. That's usually the case, I think.
Thanks.
Yeah.
Under what circumstances can you use a L1 norm versus L2 norm, and what are the trade-offs with that?
Yeah. Okay. Yeah, that's a good question. Yeah. So today I didn't talk about any L1 regularization problem. So usually, so we know the reason of using L1 regularization is that you get a sparse model. So that means for that W vector, a lot of components they are actually zeros. So people say that by doing that you can choose features. Yeah, that's what people say. But choosing features is just one thing. Another thing is about accuracy. So sometimes people ask, will L1 regularization give you better accuracy than L2? For my experiences, that's not the case. So in general, if you do L1 regularization and L2 regularization, their performance is about similar. But of course, occasionally we see some problems where L1 is better, or for some others, L2 is slightly better. But usually I think they are about similar. Yeah. Then for feature selection, then we need to compare it with other feature selection methods. Actually, sometimes if you just do simple like a t-test to check the relationship between label vectors and the features to do a ranking of features, that's already an effective feature selection method. Yeah. So again, it depends on the problem. Yeah. But I think nowadays, for some applications, people have used L1 regularization to get features. And another thing is that for some difficult or huge problems, they use this L1 to get sparsity to get a smaller model. And that's another situation to use L1. So you use sparsity, then you don't need a huge amount of memory to store the model vector W. Because in some big applications, sometimes it is difficult to store the vector W in one machine. But by taking the sparsity, then you are able to do that. That's another situation I have seen.
Just a quick question. Just a quick question. Do you have some tests on the test data set that have very small amount, maybe positive class? It's kind of a rare classification problem.
Yeah. So so in my data repository, okay, that released to the public, some of them are very balanced. So for example, the 600 gigabytes one I just mentioned, that is highly unbalanced. For the 10 million instances, only 15,000 are positive, I think. So for that one, you need to use area under precision recall curve. So when we run that problem, if you check area under ROC curve, then it still show you some good value, but that may not be real. So we switch to use area under precision recall curve, and then it can show you the difference. So that's an example. Yeah, there are some available data sets of this type.
What was the performance?
No, it cannot be accuracy, because accuracy must be 99.9999, right? So, but by using area under precision recall curve, it can be like only 10%. But you want to improve your method to 50% or 60%. Because the optimized still 100%. Yeah.
So this is the last question.
May I ask how the deep linear handle the missing values?
The answer is we don't handle missing values. So now we just assume that you don't give us any missing values.
That's why I tried before, if it has 0.
Well, you need to decide what to do at this moment. So that means we don't have a good way to handle missing values yet. Well, that's certainly another important research topic, is how to, but we haven't done a good study on that. So sorry, we haven't had any way to do. Okay, yeah, so thank you very much.
Thank you very much, Professor Lin. So I have a quick